Hello, welcome in 3CL4 Lab 3. In the first part of the lab, we'll start by finding the A and tau again that we used in Lab 2. Because these constants are specific for every unit, if you are staying on the same station that you used in Lab 2 and you are sure that your results are accurate enough, so it's fine. You can skip this part and use the values of A and tau again. But if you are not sure of whether your values are accurate or not, or you are sitting at another station, so you must find this part again, because we'll use these values to find out the resistance that we'll use in the circuit as shown in the pre-lab PDF. Okay, so we have here the same circuit of the first lab. The first one is inverter amplifier, then the summing amplifier. The output is going to the command input and the angle output is going as a feedback, and we have the same overshoot. It is the same circuit of the first lab. You can use the same circuit and make an input sinusoid and find the A and tau again as we did in lab 1, or use your values if you are sure of these values and you are using the same station. One point to mention here is the relation between the rise time and the feedback values. Okay, let's look at the oscilloscope. What we have here, we have an input of square signal going from the generator here. So we have like 3 volt, negative 3 volt. The 3 volt is telling the motor to stand at a certain angle, and the negative 3 volt is telling the motor to stand at another certain angle. So when you input the 3 volt, the motor starts to rise very quickly, but finally it is very far from the angle required, so it goes back again, goes up, down, up, down. This is what we call these oscillations, which make the overshoot that we find here. So the point here, the motor was at rest at this point. Then you said, okay, you are at angle equivalent to negative 3, go to the angle of 3 now. So the motor will start rotating very quickly, finally observes that he is much higher than the angle, goes down again, lower than the angle, goes up again, higher than the angle, down, up, down, up, down, then it settles on the angle. So we can think of this as following. If you want to go to the angle as fast as you can, then probably you will have big overshoot. If you are at this point and want to go up very quickly, then perhaps you will have very big overshoot. If you went slowly, then you will have slower overshoot. Okay, so going from here to here, as you go faster, you have less rising time. The rising time is much lower, but have bigger overshoot because you are going very fast, so you have larger overshoot. If you go slower, you'll have slower overshoot. Okay, so this part is going from here to here. It depends on what. So you are here at the angle equivalent to -3, then you go to the angle equivalent to 3. It depends on the difference, right? So we have input from here 3, and the previous location from the angle is -3. So the difference is 6. This difference is magnified or scaled by this resistance and get back to the command input. So this resistance play an important role here. The larger this resistance is, the faster you are, because this resistance amplifies the difference. So if you are in the same position, so the difference is 0, this resistance make no 0 multiplied by anything is 0. But if you change location, this resistance is very big, so it amplifies the difference and get a value to the command input so that we can track the new location. Okay, so the first part you get A and tau m. The second part depends on your calculations from the pre-lab part, which what value of this resistance which gives me 25% overshoot. We have around 40% overshoot, so we wanted to make it 25%. So perhaps, what do you think? Should we make a bigger resistance or smaller resistance? So we want smaller overshoot, so we want to go slower. So perhaps we want a smaller resistance so that it makes a smaller difference, so it makes the rising slower. So slower rising, smaller overshoot, let's see smaller resistance. You need to finish the calculation of this resistance in the pre-lab. In the lab, you can use this potentiometer, it's 100k ohm. this is fixed part, this is the variable part, so you can choose the one of the yellows and the black one. This is the, and you can change, of course, from this knob here, you can rotate left and right. So instead of this one now, I'll turn off the motor and change this resistance, fixed resistance, with the variable resistance here. Start the motor again. Now we have a bigger overshoot here. The overshoot increases here, so it means that the resistance now is larger than the original resistance. Okay, what if I try to make it smaller? Oh, it's now smaller overshoot. Look, here is many oscillations, here is one oscillation. So we look here now, we have smaller overshoot. Okay, let's make the resistance greater again, slightly bigger. Okay, we have larger overshoot again. So the higher resistance, the more overshoot we have. The smaller resistance, the smaller overshoot. If we try to decrease it slowly and slowly, can we get critically damped? It's not easy, but we can try to make it as accurate as possible. So by every time I try to make it such a bit smaller, so we have like two oscillations here. It's one oscillation, it's still one oscillation. Now it's no oscillations now, it's clear. So we now have no oscillation, no overshooting. Think of these cases. We have overshoot, critical, and under. So we have three cases. So if I continued making the resistance smaller and smaller, I get to the three cases. If I make the resistance bigger again, I get to the point of having an overshoot. Okay, so this is the second part. You must have the value of the resistance from home and try to make sure that the overshoot is around 25%. And actually you have to play with this potentiometer and try different values and see the different overshoots and show this to me. The third part is actually interesting part. It's like, okay, let's control one motor with the other motor. So actually you will work in two groups. So the group here is working with the group over there and try to connect them together, and let's see how we can do this. Okay, so this is the motor. I'll stop it now. This is the motor I'll control by hand. And I want the other motor to respond to my control signals. So this motor I'll change like this. So I'm changing the angle output. The angle output of this motor now is as if it is the signal from the generator. It is a control signal for this motor, and that is going to the other motor. So what we need to change in this setup, this is the input from the function generator. We'll remove the input from the function generator and put this one. Okay, so this is the angle output. It is now instead of my generator. Be careful of the changes. This is the angle output here. It is now instead of my generator. This is the generator now. Except this is the generator. Okay, so this command input, this is of this motor. I don't want this motor anymore. This is the command input of the other motor. If you looked at the red one, it's connected over there. It's the command input of the other motor. I put it here. I'll turn this off first. Okay, this is the command input of this motor. The ground is connected with the ground of the other motor, and this is the angle output of the other motor. I put it here. So instead of using the angle and command input of this motor, I'll use the command and angle of that motor. And the angle of this motor is actually the new input. So the angle of this motor is the new input going here. This is the difference between the angles, and this is the output. What I want to do now is change this motor and see this motor responding to that motor. Let's try to do this now for different values of resistances. Okay, let's try to move this a bit. Look, it's responding. When I rotate it, the other motor is rotating. Let's go the other direction. It's rotating. Okay, so what happens if I make the resistance a bit larger? So actually, when I make some changes in the angle here, this change is amplified and go to the other motor. So it's rotating faster now. When I make the same small changes, the other motor is making this bigger output now. Oh, that's too much, right? So what about the other angle? What happens? It's like when you make overshoot, it should decays to zeros, right? What happens if it doesn't decay, if it's keep going? That's an interesting question. Let's try to make the resistance smaller again so that the other motor stops. So again, oh, this resistance now is very small. The other motor doesn't respond at all. So we have some cases here. I'm changing the first motor, the second motor responds. One of the cases is making the angle very, very small, nearly zero. So any response here is like multiplied by zero and nothing goes there. If the angle here is moderate or slightly not zero, it's something small, the motor there began to respond. If the angle here is very big, what will happen? If very small changes will make the other motor begin to oscillate very quickly. There is different cases, and I want you to try all of these cases and try from the pre-lab and from the lecture to try to think about this. Why is this happening? Why we have these different cases? What is the relation between having the overshoot for a long time and short time with the resistance that we are changing? Please finish all your pre-lab before you come to the lab. Make sure that you calculated the resistance that you will need to use in this part. Make sure that if you have your values of A and time, that's okay, but if you don't have these values, make sure that you come and find these values before you start this lab. Thank you.